Right, so we finished last time. Let me just pull up last time's notes. I had them up just a minute ago. We finished last time talking about the rotational inertia or moment of inertia. And I gave you the formula for how to find the moment of inertia for a bunch of discrete particles. Like if you have one particle that has a distance r from an axis of rotation. So for one particle, let's say your particle's here with mass m, and here's your axis of rotation. This distance being r1, let's say m1, then I is equal to m1 r1 squared. And similarly, for a bunch of particles, we have that I was equal to m1 r1 squared plus m2 r2 squared plus dot dot dot, where r1 is the distance that mass 1 is from the axis of rotation, r2 is the distance that mass 2 is from the axis of rotation, and so on. And so I indicated that we could add up an infinite number of particles that are infinitely close to each other by using an integral. And so I wrote down the continuous version, which is just what happens when you take your particles to be infinitesimally, or to have infinitesimal mass and put them infinitesimally close to each other. Then you get that the integral, or that the rotational inertia is an integral over the object. So you're adding up all the chunks in the object of r squared times dm, where r is the distance. In this case, this is the distance that the chunk of mass is from the axis of rotation. And this dm is the mass of the infinitesimal chunk. And so you can see that this is just an infinitesimal version of this formula, because all an integral is it's just adding up an infinite number of infinitesimal things. So we're just multiplying the distance squared times the mass, and then we're adding those all up for the entire object. So the question then is how do we actually do this integral? So we do this integral the same way that we do an integral for the center of mass. So when we were finding the center of, say, the horizontal, or the x component of the center of mass vector, the way that we did it was we wrote that the center of mass, the x component of the center of mass vector was x times dm, where x is the position. It was the x coordinate. So object is bound, or what is it? So it's, you're integrating over a thing, right? Like you're adding up each chunk on the thing. It's just we don't want to write bounds for this. It'd be like integrating over a sphere, right? Or integrating over a line. Like we don't want to write bounds yet because we haven't really broken it up into coordinates. That's all. But the point is we do the exact same thing that we did to handle this integral. This was the x component of that chunk of mass. This was the mass of that chunk of mass. And then we just wrote everything in terms of coordinates. In particular, we wrote that dm is equal to lambda of x dx. And then we used the x coordinate system, and then we just did an integral. So we're going to do the same thing here. So in this, so I'm going to work a general example, and I'll show you how it all checks out. So let's do that. So suppose you have a thin rod. Oh, and by the way, the results that I'm going to ask you to calculate will only ever be one-dimensional integrals. Like they'll just be the integral along a line, because you guys don't necessarily have surface integrals handled yet, or 2D integrals and all that business. So suppose you have a thin rod with one end at x equals 0 and the other at x equals L. Also, let's put the axis of rotation. The axis of rotation is at x equals x naught, let's say. It's just some particular point. Like it could be 5 or it could be -8, whatever. It's just somewhere. And so I'm putting it at some arbitrary place so that we can work out the result in general. And the rod has linear mass density. Linear mass density, i.e. this is that lambda factor, and let's just call it lambda of x. So I'm not actually going to do the integral for you, but I'm going to set up this integral in terms of the coordinates that I've described. So we're going to use x coordinates because the rod is along the x-axis. So our coordinates, so our picture looks something like this. I don't know why it's getting thicker. There we go. So the one end is at x equals 0, let's say the left end. The right end is at x equals L. And then somewhere is an axis of rotation. So let's say the axis of rotation is this line here at x equals x naught. So the whole thing is rotating about that axis, and we'll just indicate it that way. And just that way, then we have something to reference. Let's just call this chunk of mass, that little tiny slice of the rod, that will have chunk of mass dm of x, and it will be at position x. Just that way, then we have something to reference. Now, what we're going to do is we're going to add up this distance squared times dm for every possible little slice. That's what this integral represents. You take that distance, you square it, you multiply it by that mass, and then you add all of those up. So that's really what we're going to do here. So we want to write that integral in terms of the quantities like lambda of x and x naught and all of those things, and the x coordinates. So in this case, we have I equals r squared dm. Now think about what these symbols mean. So r squared, well, actually, let's back up a little bit. Let's talk about dm. So dm, as before, dm is just the mass of that little chunk of length dx. So in particular, if the density is lambda of x, then you multiply the density by the length to get the mass, infinitesimally anyway. So we have that dm of x equals lambda of x dx. Now, by the way, putting of x there is not technically proper notation, but I think it's useful just to convey that the mass of that little chunk changes depending on where it is, right? So that of x part shouldn't really be there, but in principle, it is a function of x. It's just convention to not put it there. So just keep that in mind. Like often you'll see this without the of x part, even though it still does depend on x. Anyway, so as before, that's the case. That's what we're going to put in there for dm. And then we also need to figure out what r is. So remember that r is the distance that the chunk of mass is from the axis of rotation. So r, well, what's a distance is always a positive number. It's an absolute value. So r is the distance between this chunk of mass and the axis of rotation. Well, we can figure that out just by subtracting the two, right? Something just got erased that shouldn't have. Oh, no, that's fine. So this should be the absolute value of, say, x minus x naught. Or you could have done x naught minus x. Either way, it's fine. That is the distance, right? So conveniently, when we square this, squaring an absolute value is just like squaring the thing without the absolute values, because it's always positive regardless. So this would just be x minus x naught squared without the absolute values. And that's how it's typically written. But in principle, the distance really is an absolute value. It's always positive because distances are always positive. And then we just need to figure out what are the bounds of integration. We want to add up all of these chunks of mass, or we want to integrate over the entire rod where we're adding up the chunks of mass times the distance squared for every chunk of mass beginning on the left end all the way to the right end, or beginning wherever and ending whatever. But in terms of the coordinates that we have, we should use x coordinates because that's what our dm is in terms of. And then we should just integrate from the smallest x to the biggest x. So the bounds of the integral are from x equals 0 to x equals L. So then our integral just becomes the following. I, which is r squared dm, and I'm going to put over the whole rod. So by the way, when I say integrate over a rod, what I mean is you're adding up all the chunks only in the rod. Because sometimes later on I might write rod plus sphere, i.e. you're integrating over a rod and a sphere, and this would be an integral over the rod. You're adding up all the chunks in the rod plus an integral over the sphere. That's the only reason I write that, by the way. It is a useful means of conveying information. Oh. Okay, now it's not erasing. Now it's just writing more. There we go. Right, so the integral over the rod, well, the bounds, we know what the bounds of the rod are. It's x equals 0 to x equals L. We know what r squared is. R squared is x minus x naught squared. We know what dm is. Dm is lambda of x dx. So this is what the moment of inertia is about this axis of rotation for this particular rod. Now, depending on the situation, the formula will change. Maybe x naught is 0, in which case you wouldn't have an x naught. Maybe lambda of x is constant, in which case you just have a number there. Maybe the rod doesn't go from 0 to L, but it goes from, say, negative L to L. And so, but the point is The process of doing these integrals, or setting up these integrals anyway, amounts to finding three things. First, you figure out a way to write dm in terms of the coordinate variable and perhaps a density function. That's this step. Second step, you figure out what is the distance from that chunk of mass to the axis of rotation. Typically, distances are positive, so you might write it as an absolute value, and then you can square it. Third is just figuring out what the bounds of integration are in terms of that coordinate that you're using, and then you slap it all together. And now, this is literally just an integral that you can do. Now, you can't do it without knowing what lambda of x is, so you might have to figure that out some other way. Maybe it's given, maybe you have to compute it by, like in the homework assignment, but regardless, once you know what lambda of x is, this is just a normal everyday integral now. And it'll just give you a number, or rather a scalar quantity that has units. Yeah, so this formula does work when the mass isn't uniformly distributed. That's why lambda of x is there. So there's an example here, but I'm gonna just continue, or another example that I linked to, but I'm just gonna continue on as normal. So the next thing is to talk about principal axes. Not principal axes, principal axes. So in real life, real objects are three-dimensional, right? Phone, three-dimensional object. So they have three so based on this, the further part of the rod should have bigger eye. Yes, that's true. Further from the center of mass, and we will get to that. So a real object has three axes, or in principle has like three independent axes of rotation, right? This object could rotate, or this phone could rotate this way, it could rotate this way, or it could rotate this way. So that's three axes, and you could rearrange it so that it's like some like combination of them. But the point is you can. There are three independent ways that it could be rotated, just like how there's three independent directions that you can move in three-dimensional space. And each of those axes of rotation are going to have their own moments of inertia, right? If I had chosen a different axis, either pointing in a different direction or located at a different place, the moment of inertia would be different. So those three independent axes, the three independent axes associated with associated to a given object, given 3D object, are called principal axes. And by the way, these principal axes are defined. They're defined to be orthogonal, meaning that we don't call them principal axes if we've chosen axes that are not perpendicular to each other. Further, we can specify it's not quite a convention, but this is a name that we're giving. Like this notion of principal axes are three very specific axes, right? We wouldn't choose an axis here and then an axis, say, here. We would choose the axis that's in the middle. That's one principal axis. We would choose another axis that's in the middle. That's another principal axis. And then we would choose a third axis that's in the middle. And so those three axes, for reasons that will become clear in a little bit, those three axes all intersect at the center of mass. And they have to be orthogonal to each other, perpendicular to each other. So the principal axes, just to reiterate, the principal axes are the three axes that are perpendicular to each other and all intersect at the center of mass. That's what the principal axes are. And further, typically, the principal axes are relatively easy to guess. Like, for example, something that's like cube, that's like rectangular like this, or like a prism, it's just perpendicular to the faces. But for things that are more complicated, like, you know, a set of keys, the principal, or like a key, the principal axis might, or the principal axes might be a little bit more complicated because you have mass distributed in a funkier way. But the point is they have to be orthogonal to each other, and they all have to intersect at the, this is really hard to do, at the center of mass. So the question then is, why do we choose like what makes the center of mass intersection special? Like, why don't we choose principal axes that intersect somewhere else? So what we can note is that if you have any freely rotating body, i.e. just a thing floating in space, without any point fixed, it will naturally fix the center of mass. I.e., if you have an asteroid just freely rotating in space, and it's not moving otherwise, is there supposed to be another word after independent? axes, yes. The 3 independent axes, sorry. Right. So if you have just like an asteroid floating in space, not moving, just rotating, then the location that stays fixed is the center of mass, i.e. the center of mass will just remain in place. It'll just rotate about it across or around some axis that passes through that center of mass. And that's assuming that there are no forces on the system, of course. If there are, then the center of mass moves. Now, as for how we know that a freely rotating body fixes its center of mass in place, I will leave that up to you. But that's the reason. I'm not going to leave that up to you. That's going to be a homework question. But the reason why we picked the center of mass intersection for the principal axes is because we want to choose principal axes that describe the motion of the object independent of other types of motion, i.e. if the object were just left alone to just rotate, what kind of rotation would it undergo? And that rotation would be rotation about one of these principal axes because the center of mass remains fixed. And these principal axes will come into play later, and they do make things easier once you know what they are. So before we talk about the principal axes again, we need to back up just a little bit. Let's talk about the additivity of rotational inertia. So already you guys kind of, hopefully, have this notion that rotational inertia is kind of like mass, which means like just like how the total mass of a system is the sum of the masses of all of its constituent parts, the total rotational inertia of a system is the sum of the rotational inertia of all of its parts. So for example, suppose we have 2 blocks or 2 bodies. Suppose we have 2 bodies, both rotating about the same axis, and that's important. They have to be rotating about the same axis. So they're both rotating about the same axis. So maybe the example would be something like pen, phone. Maybe they're like on top of each other and they're both rotating this way, right? They're both rotating about that perpendicular axis. The question then is, so in principle, we could just treat those 2 separate objects as a single system. So then what is the moment of inertia, the rotational inertia of that combined system? Because we know how to find the mass of the combined system, you just add them up. So to find the rotational inertia of the combined system is fairly easy as well. In fact, it's obvious. The only caveat is that you have to know the rotational inertia of both objects about the same axis, not about the same axis relative to each other. So like this wouldn't count if this would not count, rotating like this, because they're not rotating about the same axis. Even though they're rotating the same way, the axis for the pen is up here, whereas the axis for the phone is down here. So they have to be about the same axis. So the rotational inertia of the combined system is just the sum. It's I1 plus I2, say. So another example would be, or a picture might be, if you have like a lumpy object here and you have another lumpy object here, if this object is rotating this way, and this object is also rotating that way, about the same axis of rotation, then the moments of inertia would just add together, if this is, say, I1 and this is I2, to find the moment of inertia of the whole system. So far we've talked about these principal axes, which are useful for a reason that's about to become clear. And then we've also talked about how you can add moments of inertia. The last thing to talk about to kind of join these 2 notions together is the parallel axis theorem. So the parallel axis theorem, like other theorems that we see in physics, is one of the rare things that's just mathematically true. Like Newton's law is not it's not mathematically true. It's like an empirical thing that we described. So we don't consider, so you could consider them as a single object, but that's what it means to consider it as a single system. And to find the moment of inertia of that single object, you just add the moment of inertias of the 2 pieces. I can zoom out, but I can't scroll up because I got to keep going. So the parallel axis theorem is mathematically true. It's a statement about like idealized objects. And so it answers the question, through which axis, pointing in a given direction. When I said Newton's laws are not mathematically true. What I mean is that they are empirical observations, right? Like they are true as far as we like you can't derive them from first principles is what I'm getting at. Whereas the parallel axis theorem can be derived from first principles. Yeah, sorry, I didn't mean to scare everybody. Okay, so we might have the question, through which axis pointing in a given direction has, or maybe this should be about which axis. Yeah, that's probably right. About which axis pointing in a given direction has the smallest rotational inertia. That's terrible English. I'm sorry. I'll explain what I mean in just a moment. So the point is in principle, you could ask, for example, for this phone, or you know what? I'll just for this phone. Like, right. So if I ask you, what is this? Which axis is the axis with the smallest rotational inertia for this phone? If the axis points this way, is it this axis? Is it this axis? Is it an axis in the middle? Is it, you know, an axis over here? Which axis would give the smallest rotational inertia for this phone? And so in principle, that's something you can ask. We know that the answer is the center of mass. We know that the rotational inertia is different depending on where the axis is. And so there, in principle, should be a place where the rotational inertia is smallest. So just to outline it again, if we have, say, a box, you could have an axis over here, or you could have an axis, say, here, or maybe an axis here. Any of these could, in principle, be the smallest, could be the axis about which the rotation has the smallest rotational inertia. And so we know, and we can reason this, that the rotational inertia gets bigger the further the mass is from the axis. Let me zoom back in because it's hard to write this small. Oops. No, do not exit. So this is just to say, we know that the further mass is from the axis of rotation, the more it contributes to the rotational inertia. The mass is from the axis, more it contributes. And that's just from the basic formula of the basic formula for the rotational inertia, right? The original formula we had was m1 r1 squared plus m2 r2 squared plus m3 r3 squared, and so on. And so if there's a chunk of mass, say m2, that has a really big distance from the axis of rotation, like r2, then m2 r2 squared would increase the moment of inertia a lot. Can I show the full definition of what? We're going to get to the parallel axis theorem. We're not there yet, or the full statement of the parallel axis theorem. So we know that the further mass is from the axis of rotation, the more it contributes to the moment of inertia. And so the location on an object that is the closest to all of the mass would have the smallest rotational inertia. So you'd have to find the place that is like the happy medium between all of the points of mass on the object, right? You can't have it too far to one side, because even though one side would be close, the other side would be really far away. It's supposed to be a question, but it's a really bad question. Like, it's not good English, but I hope I conveyed my meaning. And so the point is you have to find that happy medium where every point is closest to that axis. And we know what that is. This is just like an average, or a weighted average, of all of the locations of the masses, which is just another way of saying the center of mass. The center of an axis passing through the center of mass would have the smallest rotational inertia. And so the point then is that was the whole point with these principal axes. The principal axes are the places where the moment of inertia is the smallest in a given direction, because those are the axes that pass through the center of mass. So the parallel axis theorem then is a statement of how to relate the center of mass principle, or the center of mass moment of inertia, or the moment of inertia through the center of mass, through an axis passing through the center of mass, to the moment of inertia in the same about an axis in the same direction, but somewhere else, because we know that you're going to have to take the whatever the moment of inertia about some further away place is, some further away axis, that's going to be bigger than the moment of inertia about an axis passing through the center of mass. So we just so the parallel axis theorem just tells us how much we have to add to the moment of inertia through the principal axis to get the moment of inertia about some other place. So I know that's vague. Let me write up the statement, and then I'll draw a picture for you. So the parallel axis theorem states, for a given axis, parallel to and distance d from, or distance d away from an axis passing through the center of mass, the rotational inertia, I'm running out of space, rotational inertia about that new axis, or about that first axis, is, and I'm going to call it I sub nu. This is the, or I'm actually going to, I'll put nu. So this is the moment of inertia about that new axis that's parallel to the axis passing through the center of mass, but it's some distance d away from it. So the moment of inertia there, I sub nu, is equal to the moment of inertia about the axis passing through the center of mass plus m times d squared, where m is the mass of the object, or the mass of the system. So while I didn't derive this, and it's a little bit complicated to actually do this derivation, the parallel axis theorem tells you exactly how much you have to add to the moment of inertia about an axis that passes through the center of mass to get a moment of inertia anywhere else parallel to it. So the picture, and I will do my best to draw this, but the picture here is, let's say you have an object. Actually, you know what? It'd be better to do, I'll just do like a rectangle or a rectangular prism. So let's say this is the center of mass, is say right here. So the moment of inertia, whatever the moment of inertia is through that point or through that axis, we would want to find, so that's one axis. Let's say we want the moment of inertia through this axis over here. So we would find the moment of inertia about this axis, and then we would add m times d, where this distance is d, or sorry, m times d squared, where that distance is d, to get the moment of inertia about the new axis. So in fact, once you know the moment of inertia about an axis that passes through the center of mass, finding the moment of inertia about any other axis that points in the same direction is very easy. This is why it's a powerful theorem, because you only need to compute the moment of inertia really just once. You only need to do the integral once, and you do it about the center of mass, about an axis passing through the center of mass, and then you kind of get for free all of the other moments of inertia about other axes in the same direction. So again, really powerful tool. There's going to be problems like this appearing on the homework, and presumably there will be problems like this appearing on the final as well. So, you know, absorb this, do your best. I mean, I can't guarantee that, but this is a really, like, it's a really huge and useful deal, so I can only assume that that'll be the case. Now, just so then you guys have a reference, and in principle, you could derive this. It might take some calculus you don't have. I'm just going to give you a list of a few common rotational inertias. And by the way, there's a giant list on Wikipedia, and there's another rather large list in the LibreText, but this is just a reference. Some of these you could calculate because you know how to do it. Some of these might require calculus that you don't have, in which case I'm just going to give it to you. So for a uniform rod about one end, so the picture here is you have your uniform rod. God, I can't draw straight lines for my life. Uniform rod, let's say of mass m, and let's say that the axis of rotation is about this end. Let's say it has length L. Then the moment of inertia is 1/3 ml squared. For a uniform rod about the center, so the picture is much the same. We again have a uniform rod, mass m, but here our axis of rotation is about the center. Again, has length L. The moment of inertia, it's different and it's going to be smaller, right? Because the center of mass of a uniform rod is at the center. And so this one was further away from the center, so it would have a larger moment of inertia. In this case, it's 1/12 ml squared. And so that's actually the smallest moment of inertia you can have for a uniform rod about it in that direction. For a solid sphere about the center, so this one you might not be able to calculate unless you go a little bit further in the calculus than what you might currently have. So here's our solid sphere. We want to rotate it about this axis. So about the center of the solid sphere. Let's say the sphere has radius r and has mass m. Then the moment of inertia is 2/5 mr squared. No, not in principle. I mean, well, so kind of. It's derived with a volume element. You'd have to know the volume element of in spherical coordinates and then do an integral, a triple integral. Then for a solid disk or cylinder about the center, I mean, the Jacobian's related to the volume element, so I guess the answer to your question is probably yes. So here's our cylinder. The axis of rotation is this one. Let's say it has radius r and mass m. Then the moment of inertia is 1/2 mr squared. Notice, by the way, it doesn't depend on the length of the cylinder. And then for a thin cylindrical shell about the center, by the way, the reason why I'm giving you all of these ones in particular is because these ones I will either reference them in lecture, or I will use them, or you will need them for the homework. You might even need other ones for the homework, but these ones I will certainly use in lecture. So here you have about this axis, and so this is a hollow shell, has a radius of say r here and mass m. This is like a and so the moment of inertia here is just mr squared. Very simple. And so if you look at the end of the LibreText textbook, section 5.2, at the end, there's like a long list of a lot of these. And you could even Google, like go to Wikipedia and you can look up moment of inertia list or whatever. Yes, so this is for an infinitesimally thin shell. This is just the edge. It's just like in the LibreText there, it gives you the formula if you have a shell of some thickness, but I'm not going to worry about that too much right now. Right, so there's a whole lot more. It's not so hard to derive them, but it does take a little bit more calculus than you might have. So go take a look, and I also gave you some examples to work through to practice these things. Right, so that takes us through. So that's kind of the end of the story with moment of inertia. We're going to use that as a tool, but now that we know how to calculate it, now we can actually start doing stuff with it. Remember, we talked about last time that the reason we care about moment of inertia is because it kind of plays the role of mass in rotational mechanics and rotational motion. So in order to actually talk about things like rotational kinetic energy, rotational momentum, and all of those things, you need to be able to calculate this rotational inertia, which is why we spend so much time on it. But now that we have this foundation built, we can actually start talking about the dynamics of rotating objects. So let's talk about the total kinetic energy of a moving and rotating system. So we're going to consider an object that's moving both linearly, i.e. its center of mass is moving in a straight line, and it's rotating. So I will draw the simplest picture that I can. For an example, let's talk about two rocks, balls, whatever, connected by a string. And we're going to ignore gravity. This is occurring in space. Okay, that's something that we could do. So the picture that we have is maybe we have one ball of, or one rock of mass 2m connected by a string to another ball of mass m. The whole thing is rotating at some angular velocity, call it omega. And then the center of mass, which would be about a third of the way away from 2m, you guys can figure that out fairly straightforward. The center of mass is moving with some speed v cm, right? And let's say that this length here is L, just so then we have some notations. So the question you might have then, well, it's rotating, it's like spinning as it's going. You might ask, what is the kinetic energy of the system? What does that even mean? So let's just consider it. Let's just find the kinetic energy of each of its parts and add them together. So what we're going to do is we're going to find the speed of each of these rocks. We're going to find the kinetic energy of each of the rocks independently, and then we're just going to add them together. So the kinetic energy, and by the way, we're going to do that in this configuration. These speeds are going to change, but the total energy shouldn't change. So as long as so if we do this correctly, we find the kinetic energy of the top one when the top one's moving to the right. We find the kinetic energy of the bottom one when the bottom one's moving to the left. The total answer that we'll get will be the same as if we had computed it when it was horizontal and one was moving up and the other down, or if it was the other way. So the answer will be the same. The total kinetic energy doesn't change. It'll just be calculated in a little bit trickier way. So we're going to calculate in this configuration. So here, the kinetic energy of the top mass is 1/2 times 2m, twice the mass, times the velocity of the top rock. So what is the velocity of the top rock? Well, the top rock is rotating. It has some linear velocity because of its rotation, but it's also just moving with the center of mass. And in fact, we can see fairly easily that the speed here would be the speed due to the rotation plus the speed due to the motion of the center of mass. i.e., if it wasn't rotating, it would still be just moving with the center of mass speed. And if the center of mass wasn't moving, it would still be moving to the right because it's rotating. So the rotational speed, we know how to find that. We can just write that in terms of the angular velocity and the radius. And the center of mass speed is just the center of mass speed. So in this case, it's VCM, that's the center of mass speed component, plus R top times omega. R top times omega is the speed that is associated with the circular motion of the rock. And then this is just all squared. And so I'm going to just expand this out a little bit. 1/2 times 2m times VCM squared plus 2r top times omega VCM plus r top squared omega squared, right? All I did was expand. And then we can do the exact same thing for the bottom rock. Except in the case of the bottom rock, it has speed associated with the center of mass motion, but then it has or velocity to the right, but it also has velocity associated with the rotational motion to the left. So in that case, they subtract. Think about what would happen a fraction of a second later. The rocks would be like this and a little bit further on. So the bottom rock moves slightly less than the top rock. The top rock moves slightly more than the center of mass, just because of the rotation, right? Hence it's subtracted. So in this case, we would get 1/2 times m times v bottom squared, which is 1/2 m VCM squared minus 2r bottom omega VCM plus r bottom squared omega squared. So it's the same thing as this one, except with a minus sign in the middle. Okay. And now let's just double check. What is this distance? This distance, that should be L over 3, right? And this distance should be 2L over 3. So that's our top and our bottom. And we can find that out by just noting that the center of mass should be 1/3 of the way from the heavier one to the lighter one because it's 2/3 of the mass. So our top is L over 3. Our bottom is 2L over 3. All right, so we can add them together to get the total kinetic energy then. KE total, KE top plus KE bottom. I'm going to skip a bunch of algebra here because it's just writing out a lot and it'll take a lot of time. What we end up with is, so let me indicate that for you. And by the way, I would stress that you guys go home and actually make sure that this algebra is correct. We end up with 1/2 times 3m times VCm squared plus 1/2 times 2/3 ml squared times omega squared. Now let's ask the question, what is the moment of inertia about the center of mass of this system? Well, there's only two objects, so we can just do m1 times r1 squared plus m2 times r2 squared. And the distance we already know. So in this case, ICM is m1, 2m, which is 2m, times r1 squared, which is L over 3 squared, plus m, mass of the second object, times 2L over 3 squared. And this works out to be 2/3 mL squared, which is that. Which is to say that the total kinetic energy is 1/2 times the total mass, 3m is the total mass, times VCm squared, plus 1/2 times the center of mass moment of inertia times the angular speed squared. So this here is what we will call the translational kinetic energy. It's the kinetic energy. Yeah, maybe this isn't. They do not both have the same velocity. No, that was the whole point of this calculation. So this is the translational kinetic energy. It's the kinetic energy associated with the motion of the center of mass of the system. And this is the rotational kinetic energy. It's the kinetic energy associated with rotation about the center of mass of the system. Now, this is a general rule. It's always the case that you can write. We can always write for a given system that the kinetic energy, the total kinetic energy of the system, is equal to the kinetic energy due to the translational motion plus the kinetic energy due to the rotational motion. Wouldn't the distance L between them be changing if they're moving at different velocities? No, no. So their velocities are changing with time as well, but we're only looking at the velocity at this instant in time. Yeah, also they're attached together with a string. So this translational kinetic energy, like I said, is the kinetic energy of the whole system due to the whole system moving, whereas the rotational kinetic energy is the kinetic energy of rotation of the whole system about its center of mass, which is given by 1/2 I omega squared. So this is to say, you can always chunk up the kinetic energy of a system into two parts: the motion of the center of mass and the motion or the rotation about the center of mass. And that's a really useful way to divide it, because we kind of got stuck a little bit last week trying to figure out what's rotational motion and what's not, and then there's internal energy, and so all of that business. Now we have a set way that we can always do this. You can always break it up into translational kinetic energy and rotational kinetic energy, both of which are about the center of mass of the system. Now, that's always possible, but we don't always have to do it that way. You can choose to break up the total energy in another way. In particular, in some cases, an object rotates about a point fixed in space. Like the Earth rotates about the sun, and the sun is roughly fixed in space. Fixed in space, in which case, we can actually, so the example for the Earth, by the way, if we were to do it this way, we would find the speed that the Earth, we would find the speed that the Earth is moving through space, the translational speed of the center of mass, which you'd have to calculate because it's going around the sun. And then you would add the rotational energy of the Earth spinning about its own axis. Now, okay, this is actually a bad example because the Earth's also spinning and it's rotating about the sun. Maybe we would use Mercury. Mercury has one face that always faces the sun, so its rotation is only due to the actual rotating about the sun. But so there you would find its center of mass velocity, which is just its speed in a direction, and then you would multiply that by the rate or you would add to it the rotational motion associated with it very slowly turning about its own axis, which it does do because it goes around the sun, and it turns when it goes around the sun. Alternatively, we could just ask what if there's not really any like actual motion, it's just a bigger circle that it's going around. So why don't we just add up the rotation of just that bigger motion, which is exactly what we can do. We can write the total kinetic energy. If the rotation is just about a fixed point elsewhere in space, we can write the total kinetic energy as just the rotational energy, which would be 1/2 I about the fixed point, omega squared. Actually, I'm not going to write KE rotational because that has a connotation that it's about the center of mass. This is just to say that the total kinetic energy can be reframed in terms of just a rotational kinetic energy term, where the moment of inertia is measured about where it's rotating about, not about its own center of mass. So we can actually prove this fairly easily. So why is this the case? So we're going to assume that the fixed point is not the center of mass, just because if it is, it's not very interesting. So assume the fixed point is not the center of mass, and let's say that that fixed point is d units away from the center of mass. And I'll draw a picture. So the picture is you have a fixed point, and you have your object with, say, the center of mass here. And the object, maybe it's attached to a string, maybe whatever, but it rotates this way. So the center of mass follows a circular path. A circular path of radius d around the fixed point, right? That's just what it means for an object to rotate about a fixed point. So the speed of the center of mass, well, we know how to find that. The speed of the center of mass would just be the translational speed associated with the rotation. It would just be the angular speed, omega, times the distance d. Let's say that this is omega. It's omega times d. It's the radius times the angular velocity. And so what we can do is we can write the angular, we can use this formula. We can find the total kinetic energy, and then we'll be able to rewrite it in terms of this formula. So that's what we're going to do. The total kinetic energy, writing in terms of the translational and the rotational kinetic energy, would be 1/2 times mvcm squared plus 1/2 ICM omega squared, right? That's just a standard formula for the splitting it up into translational and rotational kinetic energy. We know what VCM is. VCM is omega times d plus 1/2 ICM omega squared. And so then we can just factor. We get 1/2 times md squared plus ICM times omega squared. And this term here from the parallel axis theorem, remember the parallel axis theorem is the new axis of rotation, i.e. rotating about this point here, that axis, is the center of mass moment of inertia plus the mass times the distance squared. So this is the moment of inertia about that fixed point. This is from the parallel axis theorem. Parallel axis theorem, PAT. So this just gives 1/2 the moment of inertia time about the fixed point times omega squared. So this is just to say these are not different formulas. Like these two things are not different formulas. They're just two different ways of expressing the same quantity. It's just in this case, it might be easier just to start with the moment of inertia about that fixed axis because that might be easier to compute. But at the end of the day, they're the same computation. It's just one is a simplification of the other in a very specific case. So this actually brings us to the dynamics of rolling objects, which I think is actually probably a good place to stop. I really wanted to get to the video, so. Okay, so there's a video that I'd like you guys to watch. I'll post it in the announcements that I'd like you guys to watch for next time. And then we will continue with that. It's a Walter Lewin YouTube video. It's excellent, and it's just a good demonstration that I would normally do in lecture, but I can't because I don't have the demonstration equipment. So I'm going to end lecture here.